Are you truly ready for gate calculus? Like, genuinely honest with yourself ready? Because it's incredibly easy to stare at a mountain of equations and feel like you've got it all figured out, only to completely freeze when that exam clock actually starts ticking. But hey, don't sweat it. Today, we're going to challenge your prep with a little bit of tough love and give you a fast-paced, high-yield summary of the absolutely essential problem-solving tools you're going to need.
Welcome to this explainer. I am so stoked to guide you through this material. Look, I totally get the universal struggle here. Trying to memorize giant, intimidating math formulas is rough. It literally feels like you're trying to learn a completely foreign language overnight. But I promise you, what we've built here is the ultimate visual cheat sheet. We're going to extract the core logic from our source material and lay it out so clearly that it's finally just going to click for you.
All right, let's dive into this roadmap. 1. Ordinary versus partial derivatives. 2. Euler's theorem demystified. 3. The chain rule matrix. 4. Mastering the Jacobian. And finally, 5. The integration reversal.
Starting off with Section 1, Ordinary versus Partial Derivatives.
Now, before we even think about tackling multivariable problems, we absolutely have to nail down the foundational difference in how variables are treated. Take an ordinary derivative, like y equals a function of x. It's a single variable function, so you just find dy over dx. It's exactly what we all learned back in high school. But with a partial derivative, well, things get a bit spicy. You've got a function of two variables. Say, z is a function of x and y. Here's the kicker. If you want to differentiate with respect to x, you explicitly treat y as a constant. You lock y down completely. Treat it just like the number 5 or 10. You completely ignore it as a variable and just push forward.
Moving right along to Section 2, Euler's theorem demystified. So when you're grinding through complex partial derivatives, Euler's theorem can literally save you minutes of grueling calculations. But there's a catch. You have to be dealing with a homogeneous function. So how do we actually test for that? Well, the source lecture gives us this brilliant foolproof trick. Step 1. You go into your function and replace every single x with lambda x and every y with lambda y. Step 2. Try your absolute hardest to mathematically factor that lambda completely out of the expression. Step 3, if you manage to pull lambda out to a specific power, that power, we'll call it n, is the degree of your function. And what's super cool here is that n can be a positive number, negative, 0, or even a crazy fraction.
Which brings us to the absolutely crucial formula. If you've successfully proven the function is homogeneous with degree n, Euler's theorem kicks in. It states that x times the partial derivative of u with respect to x plus y times the partial derivative of u with respect to y is exactly equal to n times your original function u. I mean, really think about why this matters. If you spot this specific structure on an exam, utilizing this formula brilliantly bypasses entire pages of manual, totally error-prone differentiation. You literally just multiply the degree by the original function and boom, you're done.
Next up, Section 3, the chain rule matrix.
Okay, so what actually happens when our variables are themselves functions of other variables? That's where the chain rule of partial derivatives steps up to the plate. Think of it kind of like a map. Say you're trying to find the derivative of your target variable z with respect to u. But wait, z depends on x and y both depend on u. So you basically have two distinct paths to reach your destination. The fundamental rule here is the addition principle. You have to differentiate along each specific path and then add those results together. So you find how z changes with x, multiply that by how x changes with u, and then add that to how z changes with y multiplied by how y changes with u. Long story short, add the paths.
That brings us to Section 4, Mastering the Jacobian. Now, even though this concept was developed well over a century ago by the mathematician Carl Jacobi, it's still an absolute heavyweight on modern engineering exams. Let's break down why this is such a big deal and how it's totally different from everything we've looked at so far. Your standard partial derivatives typically deal with just one dependent variable, but the Jacobian, it's the boss level. It handles multiple dependent variables like u and v, acting simultaneously against multiple independent variables like x and y. You're essentially capturing the combined, simultaneous rate of change of an entire system of variables all at the exact same time.
I know, that sounds incredibly chaotic, but this determinant matrix structure brings pure visual order to a really complex idea. When you're calculating the Jacobian of u and v with respect to x and y, you just set up a matrix. Look at the beautiful structure here. The rows belong to the dependent variables, so the first row is all about u and the second row is all about v. Meanwhile, the columns belong to the independent variables. The first column is differentiation with respect to x, and the second is with respect to y. You just find those 4 basic partial derivatives, plug them right into this grid, and then calculate the determinant. Simple as that.
Finally, Section 5, the integration reversal.
All right, let's totally pivot for a second. We spent this entire explainer breaking equations apart using derivatives. Now it's time to put them back together. Because integration is, fundamentally, just the collection of antiderivatives. I know, when you're staring down an indefinite integration problem, it can feel a lot like just guessing in the dark. But our source material makes a highly structured, really comforting point. There are actually only 4 core foundational methods you need to check. First, is it a standard result you should just already have memorized? Second, can you use the substitution method to simplify it? Third, do you need integration by parts for multiplied functions? Or fourth, do you need partial fractions to break down a rational expression? Seriously, when you get stuck, just run through those 4 pathways. 99% of the time, it's going to be one of them.
Let's zoom in specifically on integration by parts for a minute, because there's this golden mnemonic heuristic you absolutely have to know. ILATE. Inverse, logarithmic, algebraic, trigonometric, exponential. When you've got 2 functions being multiplied together, how do you actually know which one to pick as your first function for the formula? You just use ILATE. Whichever function type shows up first in that word, that becomes your first function. It's a remarkably simple, highly effective rule of thumb that'll keep you from just spinning your wheels in endless algebraic circles.
To wrap up this explainer, I want to leave you with a really direct, provocative challenge pulled straight from our Source Lectures Q&A. Pop quiz: what is the Jacobian of the standard polar coordinates where x equals r cosine theta and y equals r sine theta with respect to r and theta? Well, if you sit down and do the matrix math we literally just learned, the answer simplifies beautifully down to just r. The lecture points out that knowing this specific result by heart is practically mandatory for the exam. So be honest, did you know it off the top of your head? If not, hey, it might be time to review that matrix slide just one more time. Keep practicing, keep engaging with this material, and I'll see you in the next explainer.